Out of all the things that we can do with our Lewis structures after we have them, determining molecular polarity is probably the most important. Whether a molecule is polar or not determines the physical properties of that chemical and the intermolecular forces. And we'll see in our next unit that that's a huge focus in AP chemistry. So for all of these, we still start with the Lewis structure. Then we're looking for sharing of electrons and symmetry to see if the molecule is polar. So with our carbon tetrafluoride, we have polar bonds in all four directions, pulling the electrons towards the fluorine. But because of the symmetry, they're pulled equally in all four directions and cancel one another out, making the molecule nonpolar. So a good phrase to use is the symmetrical molecule, the dipoles canceling, resulting in something nonpolar. With BCl3, we also have polar bonds. Chlorine pulls the electrons more strongly than the phosphorus, so the dipoles are pointing out. Because we have a lone pair on top, it changes the shape of the molecule. The lone pair is not the polarity. The lone pair changes the shape, which causes the dipoles to not cancel. So make sure that you're really focusing on that. It's never going to be the lone pair that is the polarity. The lone pair changes the shape, makes it symmetrical potentially, and therefore a polar molecule. In this instance, with ICl3, that I to Cl bond is a large enough difference in electronegativity to be polar. But on this one, it ends up as square planar, electrons on top and bottom, and then four chlorines kind of around that middle. Well, those electrons are pulled left, right, front, and back all equally, and the dipoles cancel, making this ion nonpolar. So it's important to recognize that this is a polyatomic ion, but it is a nonpolar thing. So as a whole, there is a charge, but the bonds and the polyatomic ion itself is nonpolar. So sometimes there's some little gray area, and we'll clear that up with IMFs about ions, polarity, and nonpolar molecules. But this is a good instance of showing us that lone pairs don't make it polar necessarily. Here we have the same molecule as before. The C to H bonds are nonpolar, but O to H bonds are polar, and C to O bonds are polar. They have a big enough difference in electronegativity, and even if we don't have the exact values, there's kind of a gap between them on the periodic table, which likely means that there's a big enough difference to make them polar. The other thing to note is that it's asymmetrical. Carbon has carbon, 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 but oxygen, that's different. Oxygen has hydrogen on one side, carbon on the other, and lone pairs on the other. So there's dipoles that occur here towards my oxygen, here towards my oxygen, that are not equal and are not canceled out by other dipoles equally in other directions. So as a whole, this molecule ends up being polar. This is also a good example of organic compounds tend to have lots of carbon and hydrogen in them. That carbon to hydrogen part is nonpolar, but whenever you put an oxygen, and especially an OH in it, that becomes polar. But if the molecule's large enough, if we have a long enough chain of carbons and hydrogens, then the molecule may have some properties which are polar and some which are nonpolar, just depending how much we have of each section.